How can a machine take a plain, straight block of wood and turn it into something like this? If you only had an ordinary lathe, spinning and cutting in a straight line, you'd only ever get a perfect cylinder. To carve a spiral like this, the machine needs something more. This machine was built to solve exactly that problem. But to understand why it's designed this way, we're going to start from the very beginning, one single part at a time. And it all starts here, with one simple question: how do you make something move in a perfectly straight line? Do we need something to guide us? Rail. That is the answer to the problem. Rails don't only move in straight lines. They can bend into any shape you need. But the rail is just a map. The real motion happens inside this small block. No gap. No play. Inside, 3 problems are solved at once. First, friction. Hundreds of tiny balls circulate in a closed loop. When they reach the end, they recirculate through an internal channel. That's how it travels forever, in a fixed size block. Second, backlash. The balls are slightly oversized, pressed into the groove on assembly. That preload kills all play. Even a sudden reversal gets an instant response. Third, load. The ball rows sit at an angle, not straight up and down. Together, they carry force from all 4 sides. Upside down, sideways, it doesn't matter. One small block. 3 problems solved. The foundation of almost every precise motion in automation. But guiding it isn't enough. What actually makes it move? A sufficiently sturdy framework. The rail. The block. Step 1, complete. A motor only knows how to spin. But what we need is a straight line. Something has to stand between these 2 worlds. The simplest way, a flat belt. But under heavy load, or a sudden reversal, it slips on the pulley. Position is lost. Add teeth to the belt, meshed with a grooved pulley. Now it can't slip. Position stays accurate, no matter the load. But belts still have a limit. The longer the travel, the harder to keep it tight. For long distances, we need something else. A gear rolls directly on a rack. Nothing to sag. Nothing to slip. The trade-off, less precision than other options. And the most precise option, the ball screw. A nut with recirculating balls rides along a rotating shaft. Almost zero play. Almost zero error. The trade-off, shorter travel, lower speed. 4 ways to turn rotation into a straight line. None of them is the best. Only the right one, for the right job. The rail, the block. And now, the ball screw to drive it. The machine's first axis, complete. Bash. But what makes this screw turn? The screw needs to turn an exact number of turns, so the block stops exactly where it should. The simplest way to do that is a stepper motor. Each electrical pulse turns it by one fixed angle. Count the pulses, and you know exactly how far it turned, as long as nothing gets in the way. But there's a gap. A stepper motor never actually knows where it is. It only trusts the pulses it was sent. If a sudden force makes it slip, the controller still thinks everything went as planned. For a machine that only moves in a straight line, under light load, That gap barely matters. But this machine doesn't move simply. To carve a spiral, the spindle and the linear axis must move together in perfect sync down to a fraction of a millisecond, for hours at a time, under constantly changing cutting force. One missed step on either axis, and a perfect spiral turns into a broken, uneven line. This isn't about reaching a single point anymore. It's about always knowing exactly where you are, at every moment, an ancest of Contrius of 100 and adjusted under every load. And that's the only reason Servo exists. It constantly checks its own actual position, compares it to where it should be, and corrects itself instantly, even when cutting force changes without warning. For a machine that needs multiple axes moving in perfect sync, Servo isn't simply the better option. It's the only one. The rail, the block, the ball screw, and now a servo motor to turn it. The first axis can finally move. The screw can now turn with precision, but to carve a spiral, one axis isn't enough. The workpiece must spin thousands of times a minute stable, perfectly centered. So it needs its own rotating axis, rolling bearings to cut friction, and a multi-jaw chuck clamping symmetrically to hold it dead center. Touching that spinning workpiece is the spindle, the motor that drives the cutting tool. It spins anywhere from 10 to over 20,000 RPM, usually electric, sometimes pneumatic for extreme speeds. Spinning that fast generates serious heat, so most are cooled by an air jet or circulating water around the housing. And since the workpiece is over a meter long, one end isn't enough to hold it. The other end needs support, a tailstock, a live center, keeping it from sagging, from vibrating, through the entire cut. The rail, the block, the ball screw, the servo motor, the spindle, the cutting head, the tailstock. Each part began as a single, separate question: how to move straight, how to spin true, how to hold tight, how to stay still. Put together, they become a machine that can turn a plain, straight, round block of wood into any shape its designer can imagine. That's not magic, Grandin. That's mechanical engineering.